So finding this derivative builds off of the new material that we started with yesterday, where we saw how we could find the derivative of something like 3 to the power of x. So in finding this derivative, we have f prime of x equals, now notice that the 5 times that, that's just a constant times it. So my derivative is also going to be the same constant times that. So now it's just a matter of finding the derivative of 3 to the x, which is 3 to the x, but not only 3 to the x, 3 to the x natural log of 3. That then is our final answer. That's what we're looking for. So remember that the derivative of the 3 to the x is 3 to the x times the natural log of that 3. You always need to multiply by the natural log of the base. All right, so that was just kind of jogging our memory from where we started yesterday. I also want to take a look at where we finished yesterday, which was where you did these derivatives on your homework. So I'd like you to please check these homework answers and make sure that we're able to get the right thing. So like with this first one, you notice the very first thing we did is we changed our cube root into the same thing to the power of 1/3. Then having done that, we could then go ahead and find the derivative. Notice you're going to be using chain rule here, where we have an inner function here, and that's inside of the outer function of something to the power of 1/3. So when we do our derivative, we end up here. Now, once we've gotten here, you actually can clean it up a little bit. We didn't necessarily require that you had to clean it up, but I want us to go ahead and take a look at what it would look like if we did simplify this down at least somewhat. Because you notice here that we do have a negative exponent, and that's a fractional exponent, both of which it would be nice to be able to deal with. So I could take that negative exponent, and that means put it into the bottom of the fraction, and then the fact that it's to the power of 2/3 means that it's the cube root squared. Now I chose to write it as the cube root that was being squared. You also could have squared the 125 minus x cubed and put that inside the cube root. They both would work. But if we simplify it all the way down, this is what we'd be looking at. If you didn't take it all the way there, go ahead and make a note about what it would look like. So then on the second problem from that homework assignment, again, the first thing we want to do is we want to turn that into a fractional exponent, and then we can find our derivative again using chain rule. Notice here, my inner function is the 49 minus x squared, and outside of that, my outer function is just something to the power of 1/2. So that's using the power rule. All right, now if you got this as your final answer, again, that's perfectly fine. We didn't say that you had to simplify it strictly speaking, but then we can go ahead and simplify this further, because if I continue on, you notice I see some fractions involved, so I can go ahead and set up a fraction. When I see the negative 1/2 here, that tells me that my fraction is going to be negative and that I have a 1 on the top and a 2 on the bottom. This to the power of negative 1/2, that tells me that that's going to be on the bottom. So that's going to be the 49 minus x squared to the power of 1/2. And the negative 2x, well, that would be times negative 2x here. And as you can see, the negative here will cancel with the negative here. And we'll also be able to simplify with the 2's. Those will be able to cancel out. And we'll be able to turn the 1/2 power into a square root. One little side note on this. Can I just say, well, then I'm going to do the square root of 49 and the square root of x squared? No. Exponents do not distribute like that. So because of the subtraction inside, we just have to leave it as 49 minus x squared inside of the square root. All right, so having taken a look at that assignment, this actually relates to some of the other work that we are doing. Because you'll notice that these two equations that we were finding the derivatives of, these were actually the first couple equations from the implicit graphs 1 worksheet that we were finding the graphs for yesterday. It's the first two problems, but if we had tried to solve them first for y and then find the derivative. Basically what we did is we found the derivative explicitly there, even though those two equations, at least on the implicit graphs worksheet, are written implicitly. But the good news is, well, maybe good, maybe not, depending on how you look at it, is that we actually don't even have to solve them for y. So you see, up to this point, basically almost all the equations that we have been using have been the explicit functions. where it's solved for y equals. And that's what we did in order to be able to do the worksheet for homework last night. But we also have the implicit equations, like the ones that we were graphing in class. And we saw that some of those things get some funky looking graphs, right? Very different. And so you'll notice that this is an example of one that's written implicitly. In other words, we didn't feel the need to solve it for y or anything like that. This particular equation can be written both explicitly and implicitly. That's not true of all of them. A lot of equations can only be written implicitly. And so just like we can write an equation implicitly, we can also find their derivatives implicitly. And so that's what we're going to be looking at today, is how we actually can find the derivative implicitly without having to solve it for y. It's not only going to make our lives a little bit simpler with some of these, but even it's going to allow us to do something that we wouldn't have been able to do otherwise. And so we're going to use this as our example for how to find that derivative implicitly. Go ahead and write down this problem on your paper, and then we're going to do the work here together. All right, so to find our derivative here implicitly, basically we're going to be taking the derivative as usual. It's just that there's going to be one new wrinkle in it that we hadn't had to actually think about doing before. So first up, I'm going to do the derivative of 2x. That's simple enough, right? The derivative of 2x is just 2. And then we need to do the derivative of y cubed. Well, notice that y here is just some function of x, right? It's like we have an unknown function there. I could also have written it as, for instance, going off to this on a little tangent here, 2x equals something cubed. If I wanted to find the derivative of that equation, I could do the 2 equals, and I'd have to be using chain rule there, right? So it'd be like 3 times that something squared. But then I'd have to multiply it by the derivative of that something. And so then I'll just mark that as d over dx to remind ourselves that that's the derivative of it. So we're doing the same thing here, except it's not some unknown parentheses. We actually know that it's called y. And so we're actually using chain rule with it. And so then when I find the derivative of y cubed, it's going to give me 3y squared times the derivative. Well, what's the derivative of y? Well, how do we write the derivative of y? Just y prime. And so then this is how we can find the derivative implicitly. Is we can find the derivative of the y terms. It's just that you're actually using chain rule with it because y is some unknown function of x. And so whenever you find the derivative of a term involving y, your derivative will include y prime, and probably some other y's as well. Now, in this particular example, though, we're actually not going to be totally done. Because while we have found our derivative implicitly, there's actually one more step that we want to go through, and that is to actually figure out what y prime would equal. In other words, solve this equation for y prime. Well, you notice we got that 3y squared over that's kind of in the way, so we got to get rid of that. So we're going to divide by the 3y squared from both sides. And so then that's going to give me 2 over 3y squared equals y prime. And there we have our derivative. Now, you could have, in this case, also solve this explicitly, where you could have gone over and you could have done, solved the original equation for y, so you could have turned it into like the cube root of 2x equals y, and you then could have solved from there. But you can see that, like from last night's homework, you did a problem kind of similar to that, right? And you saw that it kind of ended up being a pain, because we got to first turn it into a fractional exponent, and then we have to actually find the derivative of that using the chain rule still, and then we got to clean that up a little bit. Notice that being able to do it implicitly saved us a bit of work there. It still got a couple steps, but it saved us some work in compared to having to do it explicitly. And remember, some are even impossible to do explicitly. Now, we went through a little bit of a process there. It would probably be useful for you to make note of what this process was. Notice this does not go on your derivative rules page, but it is part of your overall notes. So I'd write this down, or at least the key points, so that you're going to remember it going forward. All right, so then we're now just going to practice using this implicit differentiation on a few different problems here. We're going to start with this one. Now this one's fairly similar to the first one we did together, so I'm going to give you a chance to just work this one through on your own first before we do it together. All right, so to find this derivative, we are going to go ahead and do it implicitly, meaning that I'm not going to try to solve it for y first. So we're just going to go ahead and start doing the derivative. By the way, a little side note here. This is always assumed, but we're specifically finding the derivative with respect to x. Now that we're into implicit differentiation, you actually could find the derivative with respect to y and go all sorts of convoluted directions. We're just still assuming that we're finding derivatives with respect to x. All right, so to find our derivative here, we're going to do the left side, same as always. That's just going to be 18x there. And then on the right side, I'm going to use the power rule here. And so it's going to be 35y to the power of 6. But remember that I'm using chain rule here, where y is considered actually to be some function of x. And so when I do this, I need to include y and the derivative of y over here. And so it's going to be then times y prime. This is now our implicit derivative. We're not done with this problem yet, but this is the derivative. It's just that we always want to finish it by actually solving it for y prime, which means in this case dividing by the 35y to the 6. So we end up with 18x over 35y to the power of 6 that equals y prime. Can I simplify the 18 over the 35 at all? No, it doesn't look like it. And I can't simplify the x and the y to the 6, so we're done. That would be our final answer. All right, so now we continue on. Something maybe looks a little bit different, but it's all the same principles involved. Go ahead and write this one down, then start taking a look at how would you start it, and then we'll go through it from there together. All right, so when we go to find this derivative, you'll notice in order to find the derivative of sine of y, it's not just sine of x, it's sine of anything other than x, which means that the y here is playing the role of my inner function. And so then when I go and find the derivative, I'm still having to use chain rule for the derivative of sine y. So the derivative of sine is cosine, so it's going to be cosine of the outer function. And remember, when we use chain rule, whatever was inside, it stays exactly the same, so it's still going to be cosine of y there. But then I have to multiply it by the derivative of that inner function. And the derivative of the inner function here, the inner function is y, the derivative of y is y prime. So the derivative of the left side is cosine of y, y prime. We then are also taking the derivative at the same time of the right side. Now we're finding the derivative of pi x. Remember that pi is just a constant. And so it's the same as the derivative of 5x, where it's just going to equal the constant. So it just equals pi. Last step, solve it for y prime. In this case, that means dividing both sides by cosine of y. So y prime here, our derivative, is pi over cosine of y. Now, could we have done this without implicit differentiation techniques? No, at least not yet, because if you tried to do this explicitly, you would have had to do the inverse sine of both sides. And while it is possible to do that derivative, it's not with what we know so far. We haven't learned a rule for how to do the inverse sine derivative. And so we really had to use the implicit differentiation in this case. Even though it just said find the derivative, it didn't say find the derivative implicitly, we still knew that we had to use that technique. All right, next problem. Please find the derivative of this one then. Now you might be wondering, does it change anything when there's y's on the left side and y's on the right? No. You're still just going to go ahead and just start taking the derivative of the left side and the right side both. All right, so let's check out how this one works. On the left side is actually the easier side in this particular problem, because the derivative of x is just 1. and then plus the derivative of y. Well, the derivative of y is just y prime. Okay? Now we do the derivative of xy. Now, which rule do we need to use in order to find the derivative of xy? Product rule. Because notice this is x times y. And so, yes, we have to use product rule there. So I'm going to do original times derivative first. So I'm going to do the original x times the derivative of y. And the derivative of y, of course, is y prime. Then plus derivative times original. So the derivative of x is 1. And then original y is just y. So that's just going to be plus y there. All right, now that we've gotten here, we can now go ahead and finish it off. Now remember, this technically is the derivative, but we don't know what the derivative actually equals yet. So we do still need to solve it for y prime. All right, so this one can be a little bit tricky on how to start. So yeah, let's go ahead and subtract 1 from both sides. So if we do that, we have y prime equals xy prime plus y minus 1. And while we do now have a statement that says y prime equals, we also have the y prime on the right side. And we're going to need to be able to get rid of that. We need the only y prime to be the y prime that's over here on the left. Well, that means that I'd probably want to move all the y primes over to the left side then. So I'm going to go ahead and subtract the xy prime from both sides. So that gives me y prime minus xy prime equals the y minus 1. And we're closer, so this is good, but we're still not there yet, right? Yep. We're going to have to actually factor out the y prime on the left side. So the general rule when you encounter these types is move all the y primes to one side, and then if you have multiple terms, factor it out. And so I'm going to factor out the y prime, which leaves me with 1 minus x. Now that we've done that, getting the single y prime by itself is much easier because we're going to go ahead and just divide by whatever it's multiplied by, which is the 1 minus x. So we end up with y minus 1 over 1 minus x. That then is our final answer because that cannot be reduced at all from there. Next up, I'd like you to please find the derivative of this function. So when we just find the derivative implicitly, this is what we're looking at as our first step. And then from there, it's just a matter of solving it for y prime. And so we subtract the 3x squared from both sides. And then we can go ahead and divide by the 3y squared in order to be able to get y prime by itself. But you notice in this case, it can be simplified a little bit, right? So I can take that negative out front, and I can go ahead and just put that out front of the whole fraction. Of course, the 3's will also cancel out. Can I do anything to simplify the x squared over y squared? Not really, no. So it's just going to stay as y prime equals a negative x squared over y squared. And now you'll notice that this equation that we just found the derivative of should look a little familiar. This was the very first equation on your implicit graphs 1 worksheet where we were just making the graphs yesterday. We're also going to be finding some of those derivatives. So, now that you can see what the correct work looks like for this, go ahead and write this correct work on the implicit graphs 1 worksheet under the very first problem there. And then after you've done that, we're also going to come back and take a look at one other thing with this problem because we've actually found the derivative of this before, and we need to compare those results. All right, so I mentioned that you had also already found the derivative of this function before. Did you notice that? Last night's homework, the derivatives for worksheet, number 1. Remember there, you found the derivative of y equals the cube root of 125 minus x cubed. Notice that these two are the same equations, except that this one is written implicitly and this one is written explicitly. Well, when we did that work last night, and the same work that we talked about at the start of class today, we found that when we did that derivative, we ended up getting a negative x squared over the cube root of our 125 minus x cubed squared. That looks different, doesn't it? I mean, this and this are not exactly the same at the moment. But are they actually the same? Well, notice the only difference between them is actually happening down here with the y. Because there it's y squared, and here it's the cube root of 125 minus x cubed squared. Well, why would that be? Remember what y equaled? Back up here, let's do it that way, we saw that y equaled in the original problem the cube root of 125 minus x cubed. If I took that and substituted that in for y here, then we would end up with this. And so yes, it is in fact the same, and we can also see that you can take at least some implicit equations, if it can be solved for y, you can actually take those implicit equations and also then rewrite their derivative only in terms of x. You can actually get rid of the y's in some cases, because if you know what y equals, you can plug in for y at the end. All right, now the second problem on that implicit graphs worksheet, you actually already found the derivative of that one last night as well, except that one we also did explicitly. I'd like you to go ahead and find that derivative now implicitly. And yes, you can go ahead and do it right below the graph there if you wish, but go ahead and find that derivative implicitly here. All right, and so when we find this derivative, you should be finding here that y prime equals a negative x over y. That's all. A very simple little equation there. Y equals negative x over y. Make sure that that one is written correctly underneath that graph. And the cool thing is that we're going to be able to see how then we can, if we know where any xy coordinate pair is, we're then going to be able to find out what the derivative is at that point as well. So it allows us to very quickly find the derivative at any given point, even of some of those funky looking graphs. And with this particular graph, you can also see why we might want to leave the x and the y in there. Because when you graphed this, you saw that it was a circle. Well, if I said, what is the derivative of that graph at, let's say, x equals 1? You notice there's two separate points where x equals 1, right? Because it's not a function. And because of that, we'd also have to know which y coordinate we're talking about. Are we talking about the one on the top, or are we talking about the one on the bottom? Which is why we would need to plug in both an x and a y in order to know what the derivative is at that point. All right, so having done these first two derivatives off of the Implicit Graphs 1 worksheet, I'm going to go ahead and let you start working on your homework, which is to do the rest of the derivatives on the Implicit Graphs 1 worksheet.